Of what we talked about yesterday in the live lesson. Now, first of all, we'll just go back through everything that we've talked about. First thing was definition of terms. You need to know what an isotherm is. You need to know what an isothermal, isobaric, isochoric, or isometric, depending. And the one that we're going to talk about today, and also kind of the interest of what we're talking about. Adiabatic, which we talked about last chapter, and we're also going to start talking about cyclical processes. Now, with these cyclical processes, what we're going to end up going through is the fact that the amount of work that is done by a gas is going to be based upon the pressure volume diagram of that gas. It's going to be the area enclosed within it. Okay? You start with a high point, you end with a low point. But, alright, now, let's go back through here, and I apologize for my graph drawing. I still don't have very good of skills on this yet. Alright? Now, with this, pressure versus volume graph, a general isotherm or an isothermal reaction is going to have a graph that looks roughly like this. Okay. Now, the general shape of this, I apologize, it should be a much smoother curve, but the general shape of this reaction is going to roughly look like a why is it I can never find it in my notes when I need it? It's not a parabola. Hyperbola. Right? Isotherms are always going to have a hyperbolic shape. There. All right. It's going to have a hyperbolic shape, or the shape of a hyperbola. Now, remember that a hyperbola will never come all the way down to the x-axis and will never actually touch the y-axis, but it will come incredibly close. Okay? So, this is a drawing of an isotherm. The graph of a single isothermal reaction is known as an isotherm. Alright? Now, the other ones we talked about yesterday. We have a horizontal line. I should be doing this in different colors. Alright. Black is an isotherm. Oh, that is a horrible horizontal line. Alright, this would be considered an isobar because it is a drawing of an isobaric process, a situation in which the pressure remains constant throughout. It should be a horizontal line if you're actually trying to draw it nicely in your notes, but unfortunately I'm still not very good with this Moby. Alright, and the last one is a perfectly vertical line. Now in this case here, the volume remains constant. The value for it is going to be constant throughout. This is going to be, I've actually seen these called isomets much more often than I've seen them isocores. But it could be considered an isomet. I'm going to use isomet. You may deal with the word isocore in college. Okay? Now, the last one that we're going to talk about here is what's called an adiabat. Right? In an adiabatic process, well, the amount of heat entering or leaving the system is going to be zero. So what that means is that whatever changes you have in internal energy is going to equal the work done by or on the system. Okay, just going back to the first law. Okay, so with that in mind, these ones are probably the toughest to draw, because in order to draw them properly, you already need to kind of know where your start point and end point is. Couple of things with adiabatic processes. These things are idealized. It is incredibly difficult to get something that is completely adiabatic. The thing with adiabatic process, to have zero heat enter or exit the system is practically impossible. There are only two methods in which you can consider something to be adiabatic. The first one is in an incredibly well insulated container. Okay. The second situation is when this happens so unbelievably quickly that it doesn't allow heat to escape. Okay, so instead of, you know, having to have so much insulation on it, if it happens incredibly quickly, it can be approximated to be adiabatic. Now, nothing has ever been determined to be perfectly adiabatic, but it can give you a general idea. All right. Now, the thing that's tricky about these is it's not as simple as just being a basic hyperbolic shape, a horizontal line, or a vertical line. Instead, when you have adiabats, these are going to be called adiabats, I'll put these guys up in orange. An adiabat will go from one isotherm to another as some type of a curve. Okay, that right there is an adiabat. Okay, now in adiabatic processes, no heat is lost, but you do still get a relatively good region underneath this curve. Okay, the work that is done by an adiabatic process. Now this is a little bit more complex. I am going to give you the algebraic term for it right now. We will mess with this a little bit more later. It is a little bit complex because there's a couple of different things that have to happen with it. Now, the work done in an adiabatic process is equal to the initial pressure times the initial volume minus final pressure, final volume, all over, this is where it gets tricky. That is the Greek symbol gamma. Now the problem is you need to know that for the gas before you even get into it, but minus 1. Now gamma in this case right here is gamma is, well, a little bit different for different types of molecules. This is a ratio of the specific heat depending on how exactly. Alright, I need to kind of take a little bit of a side note here. Gamma is specific heat at a constant pressure divided by the specific heat at a constant volume. It turns out that depending on the situation, you are going to have a slightly different value for each one of these. We are going to talk about this a little bit further later on, but for right now, just take it at my word. Okay? Now, the gamma value for different materials is going to be slightly differing, but in general, if you have a monatomic ion or a monatomic particle, you're going to have a gamma value of around about 1.6, 1.67. If you have a diatomic particle, it's going to be closer to something like 1.40. Okay? We're not going to work with this incredibly much right now. We will come back to it later. This process is the one that's the most confusing out of everything, so we're going to skip this up. The other thing that tends to happen as well is because adiabats and isotherms tend to have fairly similar shapes, because these are the only ones that are curved, they tend to be mistaken relatively often. So because of that, we're going to kind of take these slowly. Right now, here's the part where I'm going to show off my amazing artistic prowess. Alright, so if we've got a graph of pressure versus volume, now remember, it has to be like this in order for us to solve things properly. Because pressure times volume is going to give you work. Now, let me give you the unit analysis for this, because a couple of you struggled with this on the math problems. All right, pressure is typically going to be measured in units of pascals. Volume is typically going to be measured in units of meters cubed. Now, realize that pressure can be a number of different units. Pressure can be kilopascals, can be atmospheres, can be bars, can be torrs. I am not going to make you memorize the entire list of everything. That's for college, okay? But Pascal and meters cubed. Now, volume can be in a number of different things. It could be centimeters cubed, could be liters, anything like that. But the Pascal and the meter cubed are going to be the ones that are going to give you the most direct path to an answer, okay? So, in our ideal gas equation, PV equals nRT. Right? Right. N is the number of moles, R is the rate constant, T is the temperature. The rate constant, now depending on units, but in general, the one we're going to be using is 8.31 joules per mole times Kelvin. Okay? Now, N is in moles, so moles are going to cancel with moles. Temperature is going to be in Kelvin. Kelvin's going to cancel with Kelvin. So that means the right side of my equation has units of joules. So that means by default that my left side has to. Now, it's not as direct of a situation as we may have seen in the past. All right, now, Pascal is a measurement of pressure. Now, pressure is measured in British terms. What we normally use, it'd be PSI, pounds per square inch. So you have to have a force that is being applied, in metric we're going to be using newtons, over a squared area. Newtons per meter squared. That is what a Pascal is, times meters cubed. Now, meters cubed divided by meters squared is going to cancel out. That's going to cancel 2 of those meters out of the top. So now I'm ending with units of newtons times meters. Work equals a force applied over a distance. Force times distance equals work. The units on work are newton meters or joules. So once again, I'm going to remind you again, but this is pretty much going to be the last time I remind you. Pay attention to units. Okay, please pay attention to units. Without that, you are really going to be kind of stabbing in the dark with a lot of stuff here. Right now, in general, when we're talking about graphing, all right, I'm going to draw up 2 different isotherms of the same gas. This would be a lower temperature isotherm. This would be a higher temperature isotherm. Right now, what we are most likely going to be working with is situations where there's an isothermal situation, and let's say we've got an we'll go isobaric situation as well. So, horizontal line there, and let's say we'll have another isobaric situation here. Okay, with this, the amount of work that is done by this system, and the reason that it's important that it is a cyclical process is the same exact reason that we discussed in the previous chapter. Okay, the total work done around some type of cyclical process is going to be 0, which means that you're going to have to do work to the system to get it back to the normal state to get work out of the system. That work is normally done on it by adding heat or something along those lines. Now, the situation that's interesting, or what is actually the entire reason why we study thermodynamics, we study it for this region right in here. This region right in here is what tells you how much work actually gets done by this system. Right? Now, different systems are going to be at different temperatures. There's going to be different situations at the top and the bottom lying points. So, this point right here, the area in between that curve is the work that can be done. Okay? The amount that's down here beneath it, even though this is surrounded by some of the curves, this work down here is unrealized. Right? It's stuff that we cannot use. It's stuff that is not included in that cyclical process. This is what we can actually get out right inside of these curves. Okay? So in isobaric situations with an isothermal, what's happening here? I'm going to trace it out in purple. All right? You have some situation in which the pressure is remaining constant, but the volume is increasing. You can think about that as something along the lines of pressure remains constant, volume is increasing. That could be something along the lines of an air compressor or something like that. But as the, or no, I'm sorry, not an air compressor, the area in between a piston and the cylinder head of an engine. Okay? The volume is increasing, but the pressure is remaining constant. Then after that, the temperature remains constant as the pressure decreases and volume increases as well. Alright? From there, something else is going to happen which causes the pressure to remain constant but the volume to decrease, and then the pressure will increase as the volume decreases. Now, for any of you that are interested in motors, anything along those lines, this is a rough simulation of what happens inside of the cylinder of an internal combustion engine. Okay? This would be your compression phase right here. All right? The pressure becomes very high. The volume is going to increase as you put your gasoline in there. When the gasoline goes in, or diesel fuel as it ignites, it is going to cause a quick change in the volume while at a really high pressure. As it is ignited, all right, the pressure is going to, well, drop after it's been ignited as the volume continues to increase. And then the pressure is going to steady off again as it goes down to the bottom, and then exhaust phase. Okay? Now, the area inside of here is what is the most important. I am out of time to continue recording today. I will continue this with another video lesson hopefully tomorrow morning. Go with what you've got. This is going to be something that we are working a significant amount on in the near future. So, tomorrow, or the following video lesson is going to be on how we actually can determine the space underneath the curve. Alright? Good luck. No homework. Relax. I'll see you guys when you come back in here.